In the world of machine learning, developing models that can effectively learn and apply this knowledge to new, unseen data is a significant challenge. The key to success lies in balancing two critical concepts: overfitting and model generalization. Overfitting happens when a model is too finely tuned to its training data, capturing noise and irrelevant details, which leads to poor performance on new data. On the other hand, generalization is the model's ability to function well across a variety of datasets, including those it hasn't encountered before. Overfitting, the challenge. A model becomes overfit when it performs exceptionally well on training data but struggles on unseen data. This can be compared to a student who memorizes the answers to a specific set of exam questions but doesn't understand the principles behind them. In machine learning, this translates into the model learning the noise and errors in the training data as if they were meaningful patterns, which reduces its predictive ability. Generalization, the goal. Generalization refers to the model's ability to work well on new data. A model that generalizes effectively captures the underlying patterns or trends in the training data without being misled by noise or anomalies. A well-generalized model can predict outcomes in new, unseen datasets more reliably. Strategies to improve model generalization. Several strategies can be used to prevent overfitting and enhance a model's ability to generalize. Simplifying the model. Reducing the complexity of the model can help focus on significant patterns, avoiding the capture of noise. However, oversimplifying can lead to underfitting, where the model fails to learn enough from the data. Increasing training data. More data generally leads to better generalization. Larger datasets offer a broader representation of real-world patterns, making it less likely for the model to focus on irrelevant details. Validation techniques. Using techniques like k-fold cross-validation helps assess how well a model can generalize. By training and testing the model on different subsets of data, it provides a clearer picture of its performance on unseen data. Regularization. This technique adds a penalty for overly complex models, discouraging them from capturing noise and irrelevant patterns. Early stopping. Monitoring the model's performance on a validation set and halting training when the model starts to overfit is another effective method. Data bias and fairness issues. Data bias and fairness are pressing concerns in machine learning. These issues arise when the data used to train a model is biased or unrepresentative, leading to inaccurate and unjust predictions. Bias can come in many forms, including sample bias, prejudice bias, measurement bias, or exclusion bias. Tackling data bias. Addressing data bias involves a range of strategies. Diverse data collection. Ensuring that data sets are representative of all relevant groups can help mitigate bias. Gathering diverse data ensures the model is not skewed toward one group. Regular audits and transparency. Auditing algorithms to check for bias and increasing transparency in how models make decisions are essential. This builds trust and accountability in machine learning systems. Bias mitigation techniques. Techniques such as resampling data to create balanced datasets and adjusting algorithms to compensate for biases are effective in reducing unfair outcomes. Ethical guidelines. Establishing ethical frameworks for AI development helps ensure that models remain fair and unbiased. Governance structures can further oversee the ethical application of AI technologies, computational complexity, and resource requirements. As machine learning models become more complex, the computational resources required to train and run them increase. Deep learning models, for example, often consist of millions of parameters and require vast data sets, which in turn demand significant computational power. This can make cutting-edge AI inaccessible to smaller companies and researchers due to the high cost involved. Reducing complexity and resource use. Efforts to reduce the computational demands of AI include efficient algorithms. Developing more efficient algorithms that require fewer resources is a growing area of research. Techniques like pruning and quantization can reduce the size of models without greatly affecting performance. Specialized hardware. Utilizing hardware designed specifically for AI tasks, such as GPUs, TPUs, and newer technologies like FPGAs and ASICs can boost efficiency. Edge computing. By processing data closer to where it is collected, edge computing reduces the need for large-scale data transmission. Federated learning. This method decentralizes model training, allowing data to remain on local devices, thus reducing bandwidth needs and addressing privacy concerns. Integration with existing financial systems. Incorporating machine learning, ML, and artificial intelligence, AI, into existing financial systems offers both significant opportunities and challenges. These technologies promise to enhance operational efficiency, improve accuracy, and foster innovation across various financial services, such as banking, insurance, investments, and personal finance management. However, successfully integrating these advanced technologies into traditional financial systems requires careful planning, strategic execution, and a thorough understanding of both the technological and financial landscapes. Artificial intelligence and machine learning can analyze vast amounts of data quickly and accurately, providing insights that were previously unattainable. For instance, credit scoring can be improved by using ML algorithms that incorporate non-traditional data, such as utility payments or rental history. This enhances credit evaluations, extending financial inclusion to individuals who might otherwise be overlooked. Fraud detection is another area where AI excels. Traditional fraud detection systems rely on static rules that can be bypassed by increasingly sophisticated fraud tactics. In contrast, ML models continuously learn and adapt to new fraud techniques, detecting subtle patterns that traditional systems might miss, thereby improving the security of financial transactions. Additionally, there is a cultural and technical gap between the developers of AI technologies and financial industry professionals. Financial experts must understand how AI models function and how they impact operations. Conversely, AI developers need to understand the complexities of financial systems to design solutions that meet industry standards, transparency, and explainability of machine learning models. The rise of AI and ML across industries like finance, healthcare, and public services brings benefits in efficiency and capability. However, these advancements also raise concerns about the transparency and explainability of ML models. Understanding how and why an ML model makes a particular decision is crucial, especially when those decisions significantly impact individuals' lives. Transparency in ML refers to the openness with which a model operates, while explainability ensures that its decision-making process is understandable to humans. In sensitive areas such as healthcare or finance, where decisions can affect livelihoods, transparency and explainability build trust and promote ethical AI usage. Many advanced ML models, such as those involving deep learning, function as black boxes, making decisions without a clear explanation of how they arrived at those outcomes. This is problematic in contexts like loan approvals or medical diagnostics, where decisions need to be justified. Several benefits arise from improving transparency and explainability. First, it helps build trust, as users and professionals are more likely to rely on a system they understand. Second, it facilitates regulatory compliance. In finance, for example, regulations often require that decisions made by AI be explainable. Finally, improving transparency can enhance the model's development, as clearer models allow developers to better identify and correct errors or biases. To address these issues, techniques such as simpler models, model-agnostic methods like LIME and SHAP, and feature visualization tools are increasingly being used to make ML models more interpretable. Future perspectives on overcoming these challenges. As AI continues to develop, the challenges associated with integrating ML into various fields become more apparent. However, future developments hold promising solutions. Research is ongoing into developing more efficient algorithms that require less computational power, while advancements in hardware, like specialized AI chips, could make high-powered ML applications more accessible. Data bias and fairness are receiving significant attention. Techniques are being developed to detect and correct biases in training data automatically, ensuring that AI models operate more fairly. Additionally, explainable AI is evolving to provide clearer insights into AI decisions, enhancing transparency and trust. The future of AI integration also lies in modular and cloud-based systems, which offer AI capabilities as a service, simplifying the adoption process. Ethical considerations will remain central as AI's role in society grows, ensuring that AI systems are not only powerful, but also responsible, transparent, and fair. Despite the challenges, the future of AI in finance and beyond looks optimistic. As technology advances and ethical frameworks evolve, AI will become more powerful, accessible, and beneficial to a broader range of industries and individuals.